Hello everyone, welcome back to our second session on day 3. So following from our first session, after we have the parameter estimation on the CBC events we have detected, what else we can learn from those detections. So we are happy to have Lucy Thomas here to give a lecture on the CBC science. Okay. Lucy, would you please share your screen? Thank you.
Hi, can you hear me and see my slides okay?
Yeah, everything's good. Please go ahead.
Great, thank you so much. Hi everyone, it's a pleasure to be talking to you today. I'm very sorry that I can't be there in person, but it's a pleasure to be speaking to you. My name is Lucy Thomas. I'm a postdoctoral researcher at Caltech in the United States. And I'll be talking to you today about some CBC science. Here we go. So the signals that we generally see in LIGO, as you probably have already been made aware, they sort of come in two categories. There are these short duration transient signals that I've put in this blue box on the left-hand side, and then there are some longer duration persistent gravitational wave signals. And there are also two types of ways that we can look for signals. There's modeled sources or modeled searches at the top, and then unmodeled sources at the bottom. And CBCs fall into this top left category here, where they are short duration transient signals that we do know how to model and search for. There are also continuous waves from spinning neutron stars, stochastic gravitational wave backgrounds, and other unmodeled burst sources, like from supernovae. And I believe that you will be watching or have already watched some excellent lectures on those. So in this talk today, I'm going to be talking about these CBC sources, and these are the only detected sources by LIGO so far. So let's get started. So what do we mean when we say CBCs? CBC stands for compact binary coalescences. And compact means that they're compact objects. They're very dense astrophysical objects. Binary means that there's two of them. And coalescence means that these two compact objects are merging. So in this talk, I'll be splitting it up into 4 parts. The first part is, what are compact objects? What do we mean when we say that? Part 2 is, how do these CBCs produce gravitational waves? Part 3 is, what CBC gravitational wave detections have we made with LIGO, Virgo, and CAGRA so far? And part 4 is, what can we learn about our universe using these CBC gravitational wave detections? So part 1, what are compact objects? I've put here a picture of the life cycle of a star. So a star is born from a stellar nebula, and this picture has split it up into 2 types of stars. There are average stars like our sun at the top, and then more massive stars on the bottom. And then average stars like our sun, they will go through their life cycle and become a red giant at some stage, although thankfully for us, not for a very long time. And then when they eventually die and become a planetary nebula, in the center of that planetary nebula will be left a remnant, which is the sort of leftover from the death of the star, which is a white dwarf. And this is one kind of compact object. The more massive stars, however, they, throughout their lifetime, after they've been on the main sequence, will become red supergiants. And then when they die, they do something very dramatic and they create supernovae. And depending on the mass of the massive star, if it was very massive or just quite massive, if they are just quite heavy, the remnant that will be left by the supernova is a neutron star. But if they are extremely heavy, then the supernova will leave a black hole remnant. So these are our 3 types of compact objects that can be left by the death of stars: a white dwarf from the lightest stars, heavier stars create neutron stars, and the heaviest of all stars create black holes when they die. And it's the initial mass of the star that determines which of these 3 things, which of these 3 compact objects will get left behind. So let's look at each of these in turn. A black hole, first of all, is the densest object in the universe. Not even light can escape a black hole. It's completely dark. These black holes are expected to be between 5 and 100 billion times the mass of our sun. These lower and upper masses are quite uncertain. They're just based on the best models and the observations that we have. And there are actually four kinds of black holes. I should say on the right-hand side is an artist's depiction with some science in it about how a black hole would look if it was right in front of the plane of our galaxy. So you can see the light being distorted and bent around the black hole from our galaxy. And the four types of black holes, the first is a stellar mass black hole. And those are the black holes that are formed in exactly the way that I described to you on the previous slide from the death of massive stars. They are predicted to be between 5 and about 100 times the mass of our sun, and they're formed by these dying massive stars in core collapse supernovae. The second type of black hole is an intermediate mass black hole, and these are heavier. These are between 100 and 1,000 times the mass of our sun. These, we think, are too heavy to be formed from a single dying star because stars just don't get that big. So we think that they can be formed by smaller black holes merging together. And I'll come back to this later when I talk about a gravitational wave event known as GW 190521. The third kind of black hole is a supermassive black hole, and these are between 1 million and 100 billion times the mass of our sun. These lie in the middle of galaxies. And you can see on the right-hand side here, this GIF. This is a photograph taken in radio, taken with radio telescopes of a supermassive black hole known as M87. It's in the center of a galaxy called M87. So we know these exist. We can photograph them with radio imaging. But the formation mechanism of these supermassive black holes is uncertain. We don't know if they form with the galaxy that they're in the center of, or whether they form sort of hierarchically from the mergers of smaller black holes. This is still an open question. And the fourth kind of black hole is primordial black holes. And these are hypothetically black holes that are formed soon after the Big Bang, so in the very early universe. We don't really know how heavy they are. There's a huge potential mass range, and they are one of the candidates for dark matter. These have not yet been observed. Okay, moving on to neutron stars. So these are still extremely dense objects, but they're not completely dark like a black hole. They're not quite as dense. They weigh between around 1.4 to 2.9 times the mass of our sun, although again, this mass range is very uncertain. The mass inside neutron stars is in a very extreme state of matter. So in the very core of a neutron star, all of the protons and electrons are squished together so much that they make neutrons. And neutron stars, I think, are very weird. I've put a couple of weird facts about them here. So 1 teaspoon of a neutron star would weigh 10 million tons. And some neutron stars are so compact and bend light so much, bend the photons around them so much that you can actually see the whole neutron star surface all at the same time. And on the left-hand side at the bottom, there's an image of kind of what this might look like. So where the two points at the top and bottom are the poles of the neutron star. And you can see that you can see more of the neutron star than just the half facing you that you should be able to see because of the lensing effect of the neutron star. The inner structure of neutron stars is theorized, but still unknown and uncertain, including we don't really know the relation between the mass and the density of the neutron star. This is known as the equation of state. And we don't yet know how deformable neutron star matter is. If you apply pressure to it, how much does it change its shape? And finally, the third kind of compact object is white dwarfs. These are the most common remnant for a dead star just because the less massive stars are the most common. These weigh less than 1.4 times the mass of our sun, and they have a radius comparable to Earth. So they're still very dense, but not as dense as a neutron star or black hole. And they're supported by electron degeneracy pressure. So they're actually supported by a cool quantum mechanics feature. These are not thought to be detectable by LIGO because white dwarfs in orbits, they orbit around each other in too low a frequency. So I won't really be talking very much about white dwarfs in the rest of this talk. I'll be talking about compact binaries that contain some combination of black holes and neutron stars. Okay, moving on to part 2. How do CBCs actually produce gravitational waves? But rather than directly going to talk about gravitational waves, I'm actually going to start with talking about Pythagoras' theorem, which is not an obvious place to start, but I hope you'll bear with me. So hopefully many people have seen Pythagoras' theorem on the left, that a squared plus b squared equals c squared in a right angled triangle, but maybe you didn't know that you can do this in 3D as well. So I've renamed my sides to be dx, dy, dz, and the diagonal that I'm now measuring is ds, and exactly the same kind of formula applies. I've kept the picture on the left-hand side here, but all I'm doing on the right-hand side is I'm actually relabeling things. dx is now dx1, dy is dx2, dz is dx3, and I've written out the same equation at the top, but I've put ones in place, renamed these ones to be these G1, G2, G3 components. And all I'm trying to say is that you can represent it in a slightly different way such that you can write Pythagoras' theorem as a matrix. And this matrix represents a metric. And a metric is a thing that tells us how to measure distance in some kind of space. Now let's put in some special relativity, which says that nothing can travel faster than the speed of light. So we have to include this travel time as part of our distance measurement when we're trying to measure distances in space-time. So we now have not just 3 dimensions like we did before, but we have 1 time and 3 space dimensions. And our metric, which was just the bottom right-hand corner of this matrix, now has this minus c squared at the top. And this is actually, we call this the flat metric. This has a special symbol, which is this nu. This will become important in a second. And on the right-hand side, I'm just showing a diagram of what this looks like in special relativity. So imagine that you're just a person walking through space-time. You can only move so far in space in some amount of time. So you have to stay within this light cone here. And that's what this metric is representing. Okay, now looking at some black holes. So at the top here, I've actually put a representation of the Schwarzschild metric, which is the metric, or the matrix, if you like, for a non-spinning black hole. And you can see a picture of it on the right-hand side. This metric is telling us how we measure distances in space, but very near to the black hole, the space-time seems to do a weird plunging thing. So actually this metric doesn't make sense within some radius. So there must be a black hole inside. And you can see for different compact objects slightly to the left, for a white dwarf and for a neutron star, the space-time is still being bent and can be described with a metric, but for a black hole, it's much more, and there is this last stable orbit. Okay, general relativity. I've written the equation here, which looks scary, but all you need to know about this equation is that here's the metric there, which is the measure of how we measure distance in space-time. This thing, this capital G, tells us about how space-time is curving. This capital T tells us about the matter and the mass inside our space-time. So what this is basically saying is that space-time tells matter how to move, and matter tells space-time how to curve. These two things are related. If we say that actually space-time isn't moving very much and our metric is basically flat, this special flat metric that we had before, plus some very small perturbation, you can show that gravitational waves are a natural consequence of general relativity. And they are caused by if you have masses accelerating in your space-time. The heavier your masses and the faster they're moving, the stronger your waves. And in general relativity, we have 2 different ways in which gravitational waves can stretch and squish space-time. They're 2 polarizations, which I've shown in this GIF up here. One stretches and squishes up and down and looks like a cross. The other one stretches and squishes diagonally and looks like a cross. So they're called the H plus and H cross polarizations. Okay, so now that we know gravitational waves can be made and are a feature of general relativity, how do CBCs actually make them and what do they look like? The features of the CBC are that they have 3 parts, which you may have already seen in some of your lectures previously. There's this in spiral in which the objects, the black holes or the neutron stars, are spiraling in towards each other with getting faster and faster with increasing frequency. They're giving off gravitational waves with increasing energy and frequency. Then when they finally get very close to each other, they merge. This is where the most energy is released and the 2 objects kind of coalesce and become one black hole or neutron star. And then finally, there's a ring down portion where the final object settles down into an equilibrium state, releasing gravitational waves as it does so. If the final object is a neutron star, if the 2 objects were low enough mass to then produce something that could be a neutron star, the ring down will be longer and it will include some features because the neutron star itself has matter inside which can oscillate. So it will look a little bit different to this. This one is showing a binary black hole. I have a video here, which I hope will play, which shows a representation of what I've just talked about. This is a mathematical, this is a simulation of the merger of two black holes, and the orange and the green and the yellow are the gravitational wave signal that they're giving off. So you can see the two black holes spiraling around each other. This is the in spiral. You can see the ripples in space-time, the gravitational waves. They're radiating outwards and will eventually make it to our LIGO detectors, and that's what we detect. I hope you can see that the gravitational waves are getting faster and faster during the in spiral, and they've just merged and become one object, and they're ringing off all their excess energy. Okay. So part 3, what CBC gravitational wave detections has LIGO actually made so far? These ones. So CBC detections are actually becoming quite routine for gravitational waves. We've made many, many detections so far. There were 90 gravitational wave events from our third gravitational wave transient catalog. And there are, from the first half of the fourth observing run, there are 83 detection candidates so far. And these have a wide range of properties, these detections. On the left-hand side, you can see what we call the stellar graveyard. So this is showing in a CBC, the two objects merge and they increase in mass. So the ones that are at the top of the arrows are what they've merged into. And the mass is on the y-axis, and you can see that the solar masses go right the way up to about 200 solar masses and all the way down to about 1 solar mass. So there's a really wide variety of the kinds of things that we're seeing. And I've put a screenshot of the third gravitational wave transient catalog paper here. So I'm going to talk about some notable events that we've seen so far. The first one that I can't not mention was the very first one that we ever saw. This is GW150914, which was a merger of two black holes that happened on the 14th of September 2015. And it was a comparison of the signal to our computational models showed that the signal had to be from a merger event. So you can see on the left-hand side, there's the data from the two detectors, Hanford and Livingston, at the top in red and blue. And then underneath in the second row, you can see the computational model of a merger signal that we compared it to. And then just underneath is the residual error, which is very small and doesn't really look like anything. And on the very bottom panel, there's the time and frequency domain plot of what this signal looked like. And this has the absolute characteristic, what we call chirp, of what a CBC should look like. So as time goes on, the frequency is increasing and sort of makes this rounded shape. And the reason it's called a chirp is because if you convert the frequency into sound, it sounds like a chirp. So I have a video here to demonstrate. Which I hope you can hear, but if you can't, if you just Google gravitational wave chirp, there are many, many videos, and this is probably the first thing that will come up. Okay, the next one that I have to talk about is GW170817, which is a binary neutron star event that actually had an electromagnetic counterpart that we were able to observe. And kind of the reason we were able to do that and observe the counterpart is because of Virgo. So Virgo joined the observing run just before 170817 was detected, and 3 detectors means that you get much better sky localization of where in the sky your gravitational wave signal came from. And what that means is that if you have a smaller sky area, that's less coordinates for your astronomers to go and point their telescopes at. So they're much more likely to find a counterpart. And here on the left, I've put, hopefully you can see the chirp signal in Hanford here. Livingston, it's really nice and clear. Virgo, you can't really see anything, but it is in there somewhere, I promise. And because the sky localization was so good and this event was so loud, it was observed in many electromagnetic bands with many different kinds of telescopes. It was a truly multi-messenger observation, which is fantastic. You can see here the gravitational wave, gamma ray, X-ray, UV, optical, IR, and radio signals, all of which found this event. And we were able, through the observations made on 170817, to gain new insights on how heavy elements are created, which I'll talk a little bit more about later on. So really a fantastic thing for all areas of astronomy. Next, and this is my favorite, I have to say, is 190521. This is the first direct observation of an intermediate mass black hole. So this was a merger of a 66 and 85 times the mass of our sun binary black hole. And as I said before, we think that there is an upper limit for the mass of a black hole that can be created from one single dying star. And generally, it depends who you ask, but around 65 times the mass of the sun is somewhere in that ballpark. So to see the mass of something, the merger of something which is 85 solar masses turn into something which is about 140 solar masses, this is direct evidence that you can actually make heavier black holes than that if you merge smaller black holes. And because the signal is so heavy, it's quite short. It's just a short little chirp signal that doesn't look as chirpy as the previous ones. But I've put these plots, these time frequency plots here to show you anyway. But you can see nicely in the top panel that it really does look like a merger in all three detectors, which is nice. Okay, next I'm going to talk about two events in one slide, 200105 and 200115. And these are two mergers of one neutron star and one black hole. And these events where you have one neutron star and one black hole are thought to be very rare, but amazingly, we were able to detect two of them within 10 days of each other, which is fantastic. And the final one I'm going to talk about today is one that was very recently published. It's 230529. And this was announced only a couple of weeks ago. And it's the coalescence of one neutron star, which is between 1.2 and 2 times our sun's mass, and an object between 2.5 and 4.5 times our sun. So the larger object lies in a gap, in a mass gap between what we previously thought was the maximum neutron star mass of about 2.9 to 2.7-ish solar masses, and the minimum black hole mass, which we thought was about 5 solar masses. So because of that, the nature of this object, whether it's a neutron star, a black hole, or maybe something else, is quite uncertain. And it challenges our current understanding of how stellar black holes form from stars. We thought that a black hole forming less than 5 solar masses could be impossible. So this is a really exciting event and really challenges what we think is happening in the universe. So finally, part 4, what can we learn about our universe from gravitational waves from CBCs? Because it's cool to detect these things, but actually what we want to be able to do is use the information that we gain from them to learn other things about astrophysics and to really understand our place in the universe. So the first thing is that if you detect a gravitational wave signal, you can do parameter estimation. And I know that you've already spoken a lot about this, and Saturi's lecture will have a lot more detail than I'm going to share here. But all I'll say is that the properties of compact objects change the shape of the gravitational wave. And I've put an example here. So we have a gravitational waveform model of 1509, of a binary that's like 150914 in blue. And then if you reduce the mass of that, if you make the two objects lighter, then you can see that the amplitude of your signal reduces. The green one is smaller than the blue, and also the frequency changes. These two things are not always in phase with each other. So by changing the mass, you stretch and squeeze the gravitational wave that you observe. Also, if you change how the two black holes are spinning, and what direction they're spinning and how much they're spinning, this also has an effect on the gravitational wave signal. So in the second plot, I've put an example where if you have a positive spin value, so the green, that means that your black holes are spinning very fast in the same direction as their orbit. And that has the effect that it lengthens the gravitational wave signal. And then if they're not spinning, their gravitational wave signal is kind of medium length. And then if they're spinning very fast in the opposite direction to their orbit, that shortens the gravitational wave signal. So all this to say that the properties of the compact object actually imprint themselves onto the gravitational wave signal. So then we can detangle that information from the signal and try to answer questions like, how heavy was each object? How fast are they spinning? Where and when did they merge? How far away? And if they were neutron stars, how squishy is the matter that was inside them? How deformable are those neutron stars? So one key point is that we can use CBCs to infer the properties of the individual compact objects. Another thing we can learn from CBCs is that if we have individual gravitational wave events and what we think the properties of those individual events are, we can then constrain the distribution of compact object properties across the whole population of black holes and neutron stars. So for example, if I know that I have some gravitational wave events of some masses, I might say I'm going to fit a power law to those black hole masses that I have, like in the plot on the left. So the parameters of my power law that I'm fitting is I think there'll be a minimum mass in my population. I think there'll also be a maximum mass of black hole in my population, and there'll be some kind of slope where the slope could be positive. I could have more smaller black holes, or it could be negative. I could have more smaller black holes. It could be positive. I could have more heavier black holes. But those are the three parameters that I need to infer from my population. And we can actually use what we know about the individual events to constrain these three things. Also, other questions that you can ask as if you have a population of black holes or neutron stars is, what is the lightest black hole and the heaviest neutron star mass? Is there a gap between the two? This can start to answer questions about that 230529 event that I talked about earlier. Is there actually a gap, or is it just that we haven't seen objects in this range yet? And are there hints at multiple distinct formation pathways in the masses or spins? So we know that, for example, binary black holes, they could either become black holes first and then form a binary, or they could form a binary when the stars are still alive and then possibly die and become black holes together. And does that imprint on the way does that imprint itself on the population? Can we see hints at differences between those two formation pathways in the data that we have? And finally, a thing that we can ask is, does the distribution of black hole masses change with cosmic time? And we might possibly expect it to do so, because if you don't have hierarchical mergers, if you don't have enough time for heavier black holes to be made from the mergers of smaller ones, you might expect there to be less heavy black holes earlier on in the universe. But this is a question that people are really starting to think about now that we are getting lots of observations. And I've just put here on the right, this is the most recent inferred primary mass distribution for the heavier mass of black holes in a binary. So you can see that there's already starting to look like there might be some structure in that distribution, and there might be some wiggles or some bumps that maybe with more time and given some more observations, we can really start to constrain. We can also think about the extreme matter inside neutron stars. And neutron stars are really important laboratories for the most extreme states of matter in the universe. There's no way on Earth, or maybe anywhere else in the universe for that matter, we can make the very extreme pressures and densities that exist inside a neutron star. There's just no way for us to recreate those conditions. So it's very important for us to study in any way we can what's happening inside there. So neutron star matter deforming as it goes through an in-spiral merger and ring down will actually modify the gravitational wave signal in a way that we might be able to detect. And this modification is parameterized by, we call them tidal deformabilities. That's these lambda1 and lambda2 parameters that you can see on the x and y axis of the plot on the left. So with gravitational waves from neutron stars, we can measure the neutron star tidal deformabilities and constrain the equation of state, hopefully, which is that equation between the mass and the density of a neutron star that I was talking about earlier, which is very uncertain. And actually, from the first binary neutron star observation, GW170817, this suggests that neutron stars the neutron star equation of state is soft, which maybe paradoxically means that it's not very squishy. So for a lambda, if you have a binary neutron star where the matter doesn't deform very much, if you apply pressure to it, it stays quite solid. That would correspond to a very low value of these lambdas. And you can see the darker color means that there's more evidence for this region of parameter space, given our observation of GW170817, that we have what we think is a lot more evidence for a very low tidal deformability from this observation. So actually, just from one singular binary neutron star, we've gained a lot of information and been able to rule out quite a lot of equations of state already. So this is really exciting. I'll also mention quickly, although not strictly gravitational waves, but from the counterparts that you get with binary neutron star mergers. So both kilonovae and short GRBs, which stands for gamma ray bursts, are associated with the mergers of binary neutron stars. I said earlier that 170817 was a multi-messenger event. So we saw the gravitational waves, we also saw a kilonova, and we saw a short GRB signal. And when neutron stars merge, they form heavy elements through what we call the R process. On the right-hand side, I'm showing a periodic table, and all the ones in yellow. So for example, you have gold, silver in there. I think also platinum's in there somewhere. All of these elements are thought to originate as part of this R process, and there's no other way to make them astrophysically. And when two binary neutron stars merges, when a binary neutron star merges, it produces electromagnetic radiation in the form of a kilonova, and it's in this kilonova that these elements are thought to be made. So if we can place constraints on neutron star matter, we can constrain this R process and how it works and what the rates of different reactions are. And then we can say how many heavy elements, these ones in yellow, do neutron stars actually produce? How much gold, how much silver is there in the universe that was made from binary neutron stars? I'll also talk a little bit about cosmology. So the universe is expanding. Here I put the Hubble Lemaitre law, which says that the redshift, which is some quantity which describes how much the universe is expanding, is equal to this Hubble constant divided by the speed of light times how far away the distance between 2 points is. So you can think of this as it's called the raisin bread model. So in this GIF at the bottom, imagine that you have some dough, some bread dough with some raisins inside it. And before you put this dough in the oven, your raisins will be 5 centimeters apart and 10 centimeters apart, like is in the GIF. And then after you put it in the oven and it heats up and expands, those distances will increase. So now everything is further away. Your universe, which is the bread dough, has expanded in accordance with this law. So inferring the Hubble constant means that you can infer how quickly the universe is expanding or how quickly your bread dough is rising. So you can actually do this from gravitational waves, because from gravitational waves, you get the luminosity distance, which is this distance here, the dl. And if you're lucky enough to have a binary neutron star that you've also detected an electromagnetic counterpart from that electromagnetic counterpart from the radiation, you can get this Z, this redshift. So then you can directly infer, we know what the speed of light is, you can directly infer what this H naught is. And that's exactly what we did with 170817. So in this plot, I'm showing at the bottom the constraint in this blue line that we were able to place on what we think the Hubble constant is. Also on this plot are these green and orange bands, and that is two different ways that people are able to infer the Hubble constant. So you can see that our distribution that we got from just one binary neutron star isn't as narrow as the distributions from these two independent methods, but with more and more binary neutron star measurements, we will hopefully be able to make this much narrower and try to fix what is actually a disagreement between these two other independent methods, and maybe hopefully place constraints on where actually the Hubble constant lies and resolve this Hubble constant tension as it's known. So yes, if you have an electromagnetic counterpart, you can use the redshift information to get H naught. This is called a bright siren method. But if you don't have a counterpart with electromagnetic radiation, you can still do this. What you can do is that you can get an estimate of the redshift from galaxy catalogs. You can say to yourself, well, I think that my merger would have probably come from a galaxy, because we think most objects are in galaxies. And in the distance posterior that I have for my event, I know that there are these galaxies. So you can do this probabilistically, and you can still place quite admittedly weak, but constraints on the Hubble constant from this dark siren method as well. So the key point here is that we can use CBCs to infer how fast the universe is expanding and therefore how old our universe is. And one more thing I'm going to talk about today is that we can use gravitational waves from CBCs to test general relativity. So one key question that we ask ourselves as gravitational wave astronomers is general relativity the correct description of our universe? Is it actually the right hypothesis to use? And we can test this in multiple different ways. 170817, I'm going to talk about it again. The gravitational wave and the counterpart places constraints on how fast the gravitational wave speed propagated. If you assume that the gravitational wave signal and the counterpart radiation signal were emitted at roughly the same time, we know that the light from the counterpart moves at the speed of light. So we know that because they were detected 2 seconds apart, roughly, that means that there is a very small difference or no difference at all. We can place constraints on what that difference between the gravitational wave speed and the counterpart light speed is. So far, this is consistent with general relativity, and the speed of gravity, as it's called, the speed of the gravitational wave, is consistent with the speed of light to within some very, very tiny error. I think it's about 10 to the minus 15 error. And another way that we can test general relativity is that general relativity predicts the effects of gravitational lensing. So I've put here in this picture on the left that, let's look at the top first, that if you have a gravitational wave signal coming from a CBC and on its way to the detector, it goes past a galaxy, the mass of that galaxy will distort the light and lens it, and then it might end up looking like two different signals in our detector, as shown here. And if we can find this, if we can find a lens signal, which we know came from the same source, but it's been lensed by this strong galaxy, we can test the predictions of general relativity. I should say that so far there is no evidence for a lens signal, but we're going to keep looking and see if we can find one. Finally, more ways to test general relativity. CBC waveforms that we use for detection and parameter estimation assume that general relativity is true. And this is, we think, a good assumption so far, but we can actually test if there's missing information in our waveforms to constrain if there is a deviation from GR, if actually GR is not the right theory for us to be using. And I've put here 3 different kinds of tests. There are residual tests, which look at if you subtract a best fit waveform from your signal, is there any coherent signal to noise ratio that looks like an extra signal in your data? And what you can see on the top plot is the result of a GWTC3 residual test, which shows that actually at the moment we're not seeing any coherent signal to noise ratio. We still think GR is fine. There's also in-spiral merger ring-down consistency checks. If you chop your signal for your in-spiral merger ring-down into a pre-merger part and a post-merger part and see what the masses and spins are from different parts of your signal, do they match? And if they don't match, that tells you that actually maybe there's something different happening to GR. And in the bottom plot, this is the result of a recent in-spiral merger ring-down consistency check. And you can see that the gray blob is very consistent with 0, 0, which means, yep, they're consistent, and we think GR is absolutely fine. And finally, there are tests you can do, modifications to the in-spiral of your waveform to check if you've lost any information. And again, the result of these tests so far has always been that general relativity seems to be doing very well and holding up to all of our tests. So, in summary, and to end my talk, compact objects are dead stars and they can exist in binaries. There have been many, many exciting mergers of CBCs, including black holes and neutron stars, with a huge variety of astrophysical implications. We can use gravitational waves from CBCs to infer populations, cosmology, neutron star matter, and actually test the nature of gravity itself. We are just beginning the second half of our 4th observing run, so there are so many exciting discoveries to come. Thank you so much for listening and for your attention.
Thank you very much for the nice lecture. Any questions from on-site people?
Thank you very much for the very nice talk. I'm curious about for the events of neutron star and black hole mergers. For these 3 events, especially for the case which the final mass is like within the mass gap, can we give any constraints or even rule out some scenario which the neutron star can has some QCD phase transition or some quark star model? Is it possible?
I think there are many, you can always cook up a scenario of something very exotic and where you can, what I'm trying to say is you can always build a theory where you get an object within the mass range you're looking at. I'm not sure if anyone's actually, I'm sure there are people actually testing this right now. I'm not, to my knowledge. I think it's difficult to get a neutron star in this range, whatever theory you use, especially with the constraints that come from GW 170817. But I have to say that more exotic matter, so that makes me say that I think it is probably a black hole, the heavier object, but more exotic matter, I'm not sure. I'm sure you could come up with something that lies in this mass range.
Any other questions?
I have a short question. You mentioned that to learn the population of the a black hole from the gravitational wave detection, but in reality, from the indirect evidence obtained from the EM wave observation, it seems that the population of the black hole mass measurement is different from the population we learn from the gravitational wave detection. So I just wonder if we just learn the population from the gravitational wave detection, maybe there would be some bias. What do you think about it?
Yes, absolutely. This is a great question and something I didn't go into the talk, but I could spend hours talking about. That you're right, there is some bias for the kinds of black holes that we detect. Also, there may be some bias in the way that we're inferring our population models. And I know that that second point, there are people who I think are starting to think about this and seeing how we can mitigate these biases. But with gravitational wave detectors, we are already biased because we're more likely to detect heavier things, and we're more likely to detect things where the signal stays in our sensitive frequency range for longer. So that already is a bias that we try and mitigate for when we do these population runs, but we may not be doing it properly. And I'm sure that there are similar biases that come from the electromagnetic observations where they may be more biased to certain kinds of things. So yeah, you're absolutely right. I don't have anything more concrete to say other than this is a problem.
Or your response?
All right. There are a few questions online, but because of the time, I think we can ask if Lucy can answer them in the chat. Yeah. So thanks, Lucy, again. Okay, so that will come Professor Guo-Chin Liu.
Okay, thank you very much for the invitations. So unfortunately, I cannot go to the site to give the presentation in person. So, but anyway, we can do it online. So my name is Guo-Chin Liu from Tankang University. So I will talk about this stochastic gravitational wave background. Okay, so in the beginning, maybe I need to introduce what is the stochastic gravitational wave background. So indeed, all the gravitational wave come to our side can leave some message or a signal in the detectors. They can come from something like the cosmological. Can you see my mouse? Sorry, my mouse disappeared.
Sorry, we cannot see your mouse.
Okay, anyway, so okay, so they can come from the cosmological sources, such as the inflation or the phase transition or something like the cosmic strings, and they can also come from some astrophysical source, maybe late universe, from our late universe, like the CBC or the core collapse supernovae, and also some rapidly rotating neutron star. But anyway, anything that can produce a gravitational wave, they can leave some signal in our detector. But however, most of them are too faint to be detected. Just like the button, the figure in the button shows the gravitational wave from from the mergers of the binary neutron star or the binary black holes in the left panels. But if we put the instrument noise on the top of the signal, just like the right panel, then you can see maybe only some of them can be detected individually. So those faint and unresolved sources that are the target of our stochastic background. So it is different with the CBC or burst of the kinetic wave, just like the talk in the past few days. In most of the case, we don't focus on any individual sources. We are trying to find the statistical property of those backgrounds. Okay, so let's start from this metric perturbation measured in some place x and some time t that can be expanded by the superposition of the many plane wave of the different type of polarization, like the A here, in here, HA here, and also for the different frequency F and coming from the different direction on the sky. And here HA is the coefficient of the plane wave, and the E here is the polarization tensors. Okay. So the statistical property of this stochastic gravitational wave background can be specified in terms of the moment of the HAB in the bottom. I don't see. Oh yeah, I see my mouse here. So we can we can study this the moment of the metric perturbation, like the first moment or second moment or high order moment. Or equivalently, we can study the moment of this plane wave coefficients, like the right side here. Okay, so in our previous, let me remove. Okay. Oh, in our previous LIGO collaboration papers or LIGO Virgo Kagra stochastic papers, we have assumed this background is stationary and Gaussians. We also have some additional assumption, like the gravitational wave signal are unpolarized. It means the contribution in different polarization are the same. And also we assume the noise in different detectors are uncorrelated. But for signals such with large event rate, due to this central limit theorem, the background can be Gaussian, just like the binary neutron star. They have a very high merger rate than the BPH, and also the duration of the signal lasts about a few 10 seconds. So the signal, they overlap with each others, so they looks like the Gaussian distribution. But for this binary black hole, just like in here, you can see the signal is like the intermittent, because averagely every maybe a few minutes we will see one binary black hole event, and the duration of each signal is less than 1 second. So we will see this background is intermittent. So in such kind of case, this background is non-Gaussian and non-stationary. But anyway, in previously, we have already assumed this background is Gaussian. So in such case, we don't need to consider the higher, we haven't considered any higher moment of the background. Okay. So for this Gaussian background, so the quadratic expansion value that can be characterized by this SH. This is one we call the one-sided gravitational wave strain power spectral density functions. So this is one of very important key factors, because it can directly link to the omega GW, the fractional energy density spectrum in the gravitational wave, just using this formula. And this omega GW can be defined like this, and rho c here is the critical density of our universe that make our universe flat. Okay, so So this is for the isotropic case. So for the anisotropic case, so we can drop out this last term in here and describe this statistic by this P. This is kind of the spatial distribution of the gravitational power on the sky at some certain frequency F, and depends on which one isotropic or anisotropic you want to study. Okay, so to here, maybe you would like to ask what kind of things we can learn from the backgrounds. Okay, so for the isotropic background search, the most important thing is that we want to see the energy level of the isotropic gravitational wave backgrounds. And furthermore, we can try to use this omega GW to study any non-tangential polarization background exists in our data, and also use that to study any cosmological or astrophysical model here. And because the astrophysics source may have a similar distribution as the matter in our local universe, so we do expect this gravitational wave background is anisotropic. So any we would like to see any detectable gravitational wave signal from particular direction or the particular frequencies, or something like the kinetic dipole, or we try to, or something we can see the distribution of the matter comparing with this EM wave observation. Okay, so those two studies, like isotropic search and anisotropic search, are kind of a standard measurement or standard analysis in our previous observation run. So, but very recently, people in the group, they start to think about this search of the intermittent background, and very seriously. And we are trying to construct a search algorithm based on the cross correlation or the Bayesian search to see whether we can get the information from the duty cycle or the energy density from the binary black hole. Okay, so to study this cosmological model or astrophysical model with the stochastic gravitational wave background, one thing we need to convert the information, or like the cosmological or astrophysical information, to the term omega GW by this formula. Okay, so this term gives you the spatial density of the some sources like the CBC or the inflations, and we need to integrate all the event from the low redshift to the high redshift. So this is something we calculated the omega GW for some specific source, and for all the sources we need to sum up all the contributions. So in the right panel, we just show some omega GW with some different cosmological or astrophysical model. So the blue one is given by the thorough inflation models. So you can see this model just predicted the energy level much smaller than any detection level by like either in PTA or LISA or our ground-based interferometers. And we also have some like this is a cosmic string with the tension parameter like 10 to minus 11, and we also have some first order phase transitions. And for our ground-based interferometer like LIGO and the CAGRA and the Virgo, and we can see this stellar mass CBC is kind of the most promising sources. Maybe we can detect. This is a detection level of our O3 observations, and we expect in the future we can see such kind of backgrounds. So in most of the models, we can describe this source by this power law like this. So we just give the index power index here, and some of the model we can use the broken power law. It means we can have a two power index. So by doing this, we can integrate over the frequency and get the better signal to noise level. So let's talk about this search algorithms. So we do see some the background. Oh, I lost my mouse again. Okay, so we do see this background contribute some extra power on our data, but unfortunately, those power are too faint to be distinguished from our interferometer noise. So one solution to do this is we trying to do this cross correlation of the data from the two detectors. And if the noise from the two detectors are uncorrelated, so in principle, we can suppress the noise. So the output in one detector can be written like this, guys. Okay, written like this. So here you can have some, you have your signal coupled with your detector response, and detector response can be written by this detector tensor with the polarization basis. So now we're trying to correlate the signal in two detectors like these figures. So you have the gravitational wave signal from this direction, and suppose that the separation of two detectors like delta x is here, then we will see some time delay in this figure. So after you do some calculation of this, then you can see you will see this cross correlation can be written something like this, and this gamma function is written by this detector response of the one and the two detectors, and also contains the delay of delay information. So we call this the geometric vector gamma function. So this depends on the separation of the detector or the vertex angle of the two detectors, and also some relative the orientation of the arms in the two detectors. So here we show some geometric vector. One example, this is a geometric vector of two LIGO detectors. We show the frequency f equals 0 and the f equal 200 Hertz for the real part and in the imaginary part. So we don't have any imaginary part for the f equals 0 due to the symmetries. First we notice is that we have some sensitive region on the above the sky of the two detectors, and also the other side of the Earth. So this gives the size of the field of view. So when you go to the higher frequencies, you can see many lobes. Okay, so each lobes indicate some regions have the same time delay to the two detectors, and the separation of these positive and negative lobes, it gives you some resolution of the image. Okay, if you suppose your GW sky is anisotropic, so the resolution you can simply give can be given by this simple relation. So if you have a higher frequency, you have a longer baseline, then basically you will have a better resolutions. So this is another example for the Virgo and the Kagra, and we know the two sides are much distant than the two LIGO side. So we can see even in the same frequency, we can see more lobes in here. Okay, so this is this such kind of the gamma function geometric vector is only useful for this anisotropic search. So for the isotropic backgrounds, so one thing we can do is we try to integrate all the direction for this gamma function. So we call this capital gamma function as the overlap reduction function of two detectors. So it's like the transfer function between the SH, the gravitational wave strength power, and our detected cross power, the C here. So maybe I need to rush. Okay, so in this simple chart flow, we shows the process of the analysis. So in the beginning, of course, we need to check our data quality in here, something like do the time shift analysis. We know this time delay of the gravitational wave between the ground-based interferometers is less than 0.1 second. So signal in two detected more than 1 second time shift has no any correlations. So we can use such kind of the time shift analysis to check our noise properties or find some strange noise line. Then we can do this Fourier transform, then calculate the cross correlation of the two detects in the Fourier domain. So such kind of intermediate data can be used for this anisotropic studies, and also we can use that to estimate our omega GW, and the omega GW estimated omega GW can be used to study the implication for our cosmology or the astrophysics. Okay, so since we don't have much time here today, I just focus on the green part, the isotropic search. So okay, so let me introduce the new pipeline in our stochastic. We call it PyGWB. That is the official pipeline for our isotropic search. So from last year, we start to develop a new Python-based pipeline called the PyGWB. And previously, we used the pipeline that is written in MATLAB. The reason we want to rewrite pipeline in Python is that Python was well used in gravitational wave analysis, and there are many libraries like the GWPy or the BuBi. Thanks the nice talk by Morisaki-san. And in the PyGW, we also implement such kind of the library to use. And also we have many older library in MATLAB that will not be used in future. So we try to develop new pipelines. So the documentation of the PyGWB is shown here. And of course, what can we do using this PyGWB? Of course, we can use that to analyze the data. We have used this to analyze the ER15 and also the O4A data. Of course, we can use that to run this statistic checks. We can check the consistency of the static property of the noise, and we can run this parameter estimation like the omega GW and also the power index. And of course, you can use that to simulate your own data. Okay, so in the PyGW, in the isotropic search, we are trying to calculate this estimator for each segment. The segment basically is about 192 seconds. And we need to combine the contribution from all the segment. So the estimator is defined like this. You have the cross correlation of the two detector, and you have the overlap reduction function. And S0 is defined like this. That is conversion between your strand power to the omega GW. So in the very long integration or the expectation value of this estimator, it should be the omega GW. So the uncertainty for this estimator can be defined like this. So there are some analysis parameters in here, like the duration of segment is 192 seconds, and we use the hand window for the FFT and the overlap reduction function vector. Overlap vector is about 50%. And we downsample the data from the 16K to the 4K hertz. So the Nike's frequency is about 2048. Then we try to cross-grain the frequency resolution to the 132 hertz. Now we try to analyze the frequency from the 20 to 1700 hertz. And we need to remove some artifact data, like we need to apply the gating to remove some loud glitches. So in the O3, we used the glitch information provided by the Descartes group. But in the PyGWB, now we can use the self-gating algorithm. We have a module gating module to work on this. However, this procedure, the gating procedure does not remove all non-stationaries. So we need another step called the data sigma cut to remove the uncertainty of the neighboring segment if the uncertainty differ larger than some threshold. We need to remove such kind of segment. And we also need to notch some noise lines, like the calibration lines, power lines, or some strange light detector in our time shift data. So this is our O3 isotropic result. So we have combined all the omega GW estimate by all the observed segments, including O1 and the O2, and also the baseline contains the Virgo in O3, except those are gated and also are data sigma cut. So the two solid line here curve, they are the uncertainty of the estimator, and you have some blue dot or the curve here is the data, the measurement of the estimators. Basically, we found that this spectrum is consistent with the expectation from the uncorrelated Gaussian noise. I think this is the conclusion of our O3 observations. And since we don't have any detection on the background, so we can give the upper limit on the omega GW at the f equal 25 Hertz. So you can see there are so different power index in here, and given the upper limit of the omega GW in 25 Hertz. So for different priors, and in O2 we have those value, and in O3 we can see a large improvement if we include the O3 data. And this is the parameter expansion result, and you can see the alpha just follow the prior we used, and this contour we don't see any omega GW in the 25 Hertz, so we just place something like the upper limit on that. So I think this is the last page in my talk. So here we just give you some prediction of the omega GW by some models and some projected sensitivity in the future. So here we have some models predict the omega GW for the binary black hole here and the binary neutron star here. And we have some, we don't have very many very clear model for the neutron star and the binary hole so far. So we just put the upper limit of the curves. So if you sum everything together, then you get this dash line here. And we put the sensitivity or the observation level for the O2 and the O3 and decide HLV and decide A+. So it seems in the designed A+ sensitivity, we are possible to detect such kind of backgrounds. So I'm sorry I take too much time, and I think I just stop here. And thank you very much for your attention.
Thank you very much. We have time for just one quick question from on site. Oh, okay.
Thank you for your talking. I have a small question for stochastic search or pipeline of PyGWB. So why do you choose segment of length of segment 192?
You mean here?
Oh, yes.
Okay. This okay. As I showed in here, so we should have some data. We should generate data that can be used for the anisotropic search. There are several reasons actually. So we cannot choose a very long duration because the sky will change during this period. So if we take a very long period, then such kind of cross correlation cannot be used for the anisotropic studies. And we also don't want to choose a very short duration because based on the first Fourier transform, short duration means the wider frequency resolution. So when you notch the lines, like the calibration lines or the power lines, then maybe you lost too much if you choose a very wide frequency resolutions. So this is kind of parameter we have tried to study. This is in the 004 we have studied different duration of segments like the 32 second, the 128 seconds. But eventually we think this is kind of good choice for our study.
Okay, thank you.
Okay, I think we have to conclude this session now. So thank you very much, Professor Liu. So in the afternoon, we'll continue with the hands-on session. So yeah, at 2 o'clock. But before we go, first, that thanks all of the speakers and mentors for in the 3 days for this workshop. And also, without the support of the staffs from NMNS, we cannot have this happening. So let's thank them too. And finally, we have to thank for the organizers from the Open Data team, especially Jonah and Lupin here. Yeah, it would be impossible to have all this without their efforts. All right. Do you want to close this session? Okay. If no, let's come back at 2 o'clock. Okay. Thank you very much.